This facility captures thousands of tons of CO2, which is then liquefied and shipped globally for secure geological storage. The process begins with capturing atmospheric carbon, which is then liquefied through cryogenic cooling and transported globally.
Welcome to the 5th module of our CCUS Masterclass series. In this video, we will explore maritime LCO2 shipping, deconstructing the thermodynamics, naval architecture, and logistics of transporting liquid carbon dioxide. Decarbonizing midstream transport is essential. The global fleet rationale centers on connecting industrial point sources to distant storage. Retrofitting existing carriers offers a significant opportunity to accelerate deployment and bypass the long lead times of building new pipelines. Our focus today covers 3 key instructional milestones: understanding the logistics of shipping networks, the complex thermodynamics of liquid CO2, and the naval architecture requirements for vessel conversion. We begin with Part 1, focusing on the logistical rationale for shifting to maritime transport. When comparing pipelines to maritime shipping, pipelines are fixed, high-capacity assets with sunk costs. Maritime transport, however, provides dynamic flexibility, allowing operators to adjust routes and scale capital costs to meet changing market needs. For longer transits exceeding 500 kilometers, maritime shipping becomes highly cost-competitive. It offers a lower capital expenditure ceiling than the alternative of constructing extensive long-distance offshore pipelines. Global routes provide geopolitical benefits through dynamic rerouting, bypassing complex maritime zones. It also offers regulatory resilience by enabling redirection of exports and allows hub-and-spoke models to connect smaller emitters to centralized collection terminals. Maritime transport supports agile capacity planning. With an 18-month lead time for ship delivery, fleet expansion can be scaled incrementally to match the commissioning schedules of actual capture plants, reducing risk. For offshore loading and injection, vessels use subsea anchor moorings to connect directly to sequestration fields. Onboard systems handle the heating and compression required to inject the fluid into saline aquifers. Part 2 of our discussion addresses the critical topic of phase thermodynamics. A primary constraint is the triple-point boundary. Liquid CO2 cannot exist at atmospheric pressure, so operating conditions must be strictly maintained to prevent localized dry ice nucleation and ensure safe cargo transit. The operating state of LCO2 varies by pressure range, affecting design temperature, density, and the required vessel containment systems, ranging from lightweight to very heavy structures. By utilizing low-pressure cryogenic conditions, we can achieve a 12% density premium compared to medium-pressure alternatives, which significantly maximizes payload capacity and lowers overall operational costs. We must also consider the boil-off thermodynamic reality. CO2 has a low latent heat of vaporization, meaning external thermal ingress can initiate cargo boiling. This requires robust insulation and reliquefaction systems to prevent carbon losses. Finally, transient surges like hydraulic water hammer from valve closures or vapor cavity collapse from pressure waves pose physical risks to piping and components, requiring careful engineering design to mitigate. We now examine the impact of impurities on phase stability. Non-condensable gases like nitrogen or hydrogen can shift the bubble point, while water traces must be kept strictly below 10 ppm to prevent ice blockage in cryogenic valves. This brings us to Part 3 of the video, covering the essential naval architecture requirements for these specialized vessels. For CO2 carriers, Type C pressure vessels are the industry standard. Unlike atmospheric tanks, these are engineered to withstand the dynamic pressure swings, ranging from 5 to 45 bars, encountered during ocean transport. Bi-lobe tank designs are preferred for optimizing space. By merging 2 cylinders, they increase volumetric efficiency by up to 25%. They also incorporate integrated bulkheads for structural stiffness and resilient saddle mounts to isolate thermal shrinkage. Retrofitting oil tankers for CO2 requires significant structural modification. Because these pressure vessels create highly concentrated point loads, the ship's lower double-bottom girder system must be extensively reinforced to maintain structural integrity. Vessel stability is also a key factor. Liquid CO2 is significantly denser than crude oil, which shifts the ship's center of gravity upward. This necessitates ballast adjustments or widening wing tanks to ensure roll stability. Space utilization is constrained by the round geometry of Type C tanks. In square cargo holds, this limits volumetric efficiency to approximately 62%, alongside a required 5% ullage margin for safety. Material selection is critical. Standard ship steels become brittle at cryogenic temperatures. We must use specialized carbon-manganese alloys, with mandatory post-weld heat treatment to relieve residual stress after fabrication. Modern carriers are increasingly adopting dual-fuel propulsion and ammonia-prepared structures. These innovations allow the use of boil-off gas for fuel, further reducing the vessel's overall emissions footprint. The final section of this video details the operational procedures essential for safe cargo handling. Standard loading involves a precise sequence: inerting the tanks with nitrogen, gassing up to increase pressure above the triple point, controlled cool down to prevent thermal shock, and final loading while maintaining a safe vapor margin. Boil-off management is continuous. Vapor is drawn off, compressed, and cooled. These reliquefaction plants are power-intensive, often requiring upgrades to a vessel's auxiliary diesel generators during the initial retrofit. Operators must strictly avoid depressurization. If tank pressure drops, the cargo can flash into dry ice, which risks plugging pumps and valves. Maintaining back pressure above 5.5 bars is non-negotiable. For discharge, ships utilize submerged deep well pumps. These systems are designed to maintain sufficient suction head to prevent cavitation, which could otherwise vaporize the liquid cargo at the impeller and cause equipment damage. Finally, safety is supported by automated emergency shutdown protocols, including dynamic positioning interlocks and high-pressure dry brake couplings that ensure safe separation during offshore transfer operations. Now we transition to our fifth module's final focus: class and regulation. Navigating the legal landscape is as critical as the engineering itself when deploying maritime CO2 infrastructure. The IGC code, or International Code for the Construction and Equipment of Ships Carrying Liquefied Gases in Bulk, is the primary regulatory framework. It dictates the safety standards and class notations required for legal operation of LCO2 carriers. When looking at capital expenditure, conversion of existing hulls can provide significant savings of up to $30 million compared to new builds. Furthermore, it avoids shipyard backlogs, allowing operators to deploy capacity up to 18 months faster to meet regulatory targets. Starting in 2026, the EU ETS mandates 100% compliance for maritime emissions. For operators, this means that transitioning to low-carbon propulsion or implementing carbon capture is no longer a strategic choice, but a requirement for fiscal survival. This concludes our presentation on Module 5. Thank you for your participation and for engaging with these critical technical and regulatory challenges in maritime decarbonization. If you are interested in further collaboration on research, pilot designs, or technical training, please reach out via the contact details provided on screen. Thank you for your time.